if you have three switches, and each switch can be either on or off, then the set of possible ways to set the switches can be represented easily by a tree. Switch could be on or it could be off. So let's let the on or off here stand for the possibilities for the first switch. So the first switch you throw is either on or off. And then the second switch could be either on or off. So if the first switch is on, the second can be on or off. If the first switch is off, the second could be on or off. So there are, at this point, four possibilities for the first two switches: on, off, on, off. And then there are, again, two possibilities for the third switch, so that for every possible combination in the first two switches, you have two possibilities for the third. So that's three switches with no restriction on whether a given switch is on or off. Now, in this case, the fundamental counting principle holds. And the fundamental counting principle says that the number of choices you have at each step is always the same. What we're going to say is the question. We're going to ask the three questions. Okay, how many choices are there for the first switch? Well, there are two. It's either on or off. For the second switch, how many choices? Well, there are two. It's either on or off. And of course, each of those two choices would apply to either of the choices of the first switch. What about the third switch? Well, it's either on or off. So there are two possibilities at each step. Through the first switch, you have two choices. Through the second switch, you have two choices. Through the third switch, you have two choices. And in this case, you're going to say that there are therefore 2 times 2 times 2, or 8 ways to set switches. Now, I want you to think about the first problem on the 1501-15, or the January 15th class. The first question that we addressed was what would be the set of possible outcomes, or the sample space, if you have the restriction that you can't have two ons in a row. Okay, so you should work that out. Maybe draw the tree diagram, maybe list the possibilities. And you should pause and work that out if you haven't already done that in class. Okay, so, well, here we go. 3 switches, 2 adjacent can't be on. You can't have 2 adjacent switches on. So the first switch could be either on or off. There's no restriction at that point. The second switch, well, if the first switch is on, the second switch can't be on. It has to be off, because if the second switch was on, you'd have 2 of them on, 2 adjacent switches being on, and we're not allowing that. Okay. Now, if the first switch is off, then the second switch could be either on or off. It would be okay either way, because you would not at this point have 2 adjacent switches being on. So if the first switch is off, you have either of these 2 choices for the second. Okay, now, if the first is on and the second is off, then what? Well, then the third switch can be either on or off, because the second switch being off, the second and third switch could not both be on, so you have that possibility. If the second switch is on, the third switch has to be off. If the second switch is off, then the third switch could be either on or off. So now we have a tree that represents the 5 different possibilities, with the restriction that 2 adjacent switches can't be on. And this example illustrates a case where the fundamental counting principle does not apply. How many choices are there for the first switch? Well, there are 2. It could be on or off. How many choices are there for the second? Well, that depends on what you did on the first. If the first switch was on, then you only have 1 choice for the second. If the first switch was off, you have 2 possible choices for the second. And you can't answer the question, how many possible choices are there for the second switch, without knowing what happened on the first. So There are two choices for the first. Number of choices for the second depends on the choice made for the first. If the first is on, the second has to be off. If the first is off, the second could be either. You can't answer the question, how many choices are there for the first? How many choices then are there for the second? You can't have just one answer. The answer depends, which means the fundamental counting principle doesn't apply. Fundamental counting principle says the number of choices at each step of the process doesn't depend on what happened previously. The number of choices is the same no matter what happened previously.